Okay, shall I start, sir?
Yes, please, Rajesh.
Okay. So, welcome to my seminar talk on accelerating computation of Steiner trees on GPU. Just a second, I'll also do. I am Rajesh, research scholar at Computer Science Department, IIT Madras. First up, I'd like to thank my advisors. Without their support, this work would not have got completed and published. And I would like to thank the server machine and also the TCS and PACE lab members for their discussions. Right. Next, I would like to thank upon the space programming challenge which introduced me to this Steiner tree problem. So this work which we are going to talk about in the next 50 minutes is published in IJPP journal. Right. Okay, let's get started with the outline. So the talk is categorized into three parts. So the first part will be the introduction and the example and the algorithm description, and the second part of the talk is like what are the challenges and like what are the design choice we had in parallelizing this algorithm and the CPU implementation along with the optimization. So third part is like how did we implement this on GPU along with the optimization for shortest path thing and also the overall optimization for this algorithm. So finally we'll conclude with the experimental results and the summary. Okay, what is Steiner tree problem? So in informal terms, given an undirected graph and W is the non-negative edge weights and we have a subset of vertices which are called terminals. So what is the output? We need to output a tree with all terminals. So what is the goal here? Our goal is to minimize the weight of the tree. So the tree is here, we call it as Steiner tree because it contains all the terminals and possibly 0 or more non-terminals. So first question that comes to our mind is what are terminals? So terminals are special vertices which must be present in the tree. So then what are non-terminals? Non-terminals are Steiner vertices or also called Steiner vertices, which are generally included in the tree to minimize the overall weight of the resultant tree. Right. So we use standard graph theoretic notation N and M for this. In addition to it, we use K to denote the number of terminals. Right. So where is Steiner tree applicable? So Steiner tree is okay. The applications of Steiner tree are everywhere. So in case of wire routing in VLSI design, just a minute. Okay. So it is applied everywhere as right from VLSI design and also in network routing in wireless networks. So yeah. So to get started, we'll take a small example and then understand what is Steiner tree. So given a graph G with edge weighted function and terminal set, so we have to output a connected subgraph such that we give out a minimum weighted tree with all the terminals. So in this example, the red colored vertices are the terminal vertices and we need to give out a minimum weighted tree, which is the minimum Steiner tree in our case. So which is the thick edges which are in black. So the weight of the Steiner tree here is 6, right? So for a minute it might look like the MST could actually solve this problem, but yes, the intuition is right, but let's modify this example a little bit and see how the MST algorithm can perform in this scenario. So the optimal for this instance is also same as 16 as in the previous case, whereas the MST would output something larger weighted tree in this case. So okay, yes, the takeaway here is the MST solution is a valid feasible solution for the Steiner tree problem. However, the solution can be arbitrarily bad because for example, in the previous case we have added minimum weight, lesser weight edges to make the MST algorithm perform bad. So there are two special case for this Steiner tree problem. When the terminal set is just two vertices, then the Steiner tree is actually the shortest path distance between the two vertices, right? Yeah. So when the terminal set is all the vertices, then the MST itself is the Steiner tree for the instance. Right.
So Rajesh, just for the interest of maybe non-CS people, MST means minimum span tree, right?
Yes, minimum spanning tree. Yeah, sorry for that. Okay. Okay, let's both these shortest path and the minimum spanning tree is solvable in polynomial time. So let's say if we plot the terminal size in the number line from 2 to n, basically the n points are actually solvable in polynomial time, whereas the intermediate gray thing is not. So in general, STP is Steiner tree problem is NP hard in our case. Okay, so what is the way out? One way out is the approximation algorithm. So yeah, so so there's no polynomial time algorithm for this problem to find out the optimal solution unless p equal to np. So what could be a naive solution would be, so enumerating all spanning trees. Again, this enumeration of a spanning tree is a costly operation. So one way out is, as we said earlier, it's the approximation algorithm. So what is an approximation algorithm? Approximation algorithm runs in polynomial time, right? Okay, so it outputs an approximate solution with some guarantee, for example 2 or some constant. For example, the solution output by the algorithm will be 2 times away from the optimum or some constant times away from the optimum, or maybe function of n as well. So there are several approximation algorithm for Steiner tree. There are one by Melhorn, one by Robinson and Zalewski, and one by Cow, Markovsky and Berman. So we choose Curve, Markovsky and Berman algorithm for our implementation, and we will be using the abbreviation for this algorithm as KMB in a shorter format throughout the presentation. So this is again a 2 approximation algorithm. So the solution produced by this algorithm is at most twice of the optimum solution. So the OPT means here the optimum solution value. Okay, so let's compare where do we stand with respect to the related work. So there are 3 works that are listed. One is the PACE winners code, and the second one is the Open Graph Drawing Frameworks implementation of KMB, which is a published work in Journal of Experimental Algorithms. So the other is the GPU implementation of a CUDA star algorithm. So all these algorithms, the first 2 algorithms runs on CPU, whereas the second one, the third one runs on GPU. However, the third one does not run on larger set of vertices. Whereas the first 2 implementation works on larger set of larger set of terminals when k is greater than 128. Right, so we don't have source code for this to compare this qualitatively, whereas we do have source code for the rest of the 2. So we were able to compare the average solution quality and the average time taken for these baselines with respect to our work. So what did we do? We actually built both the CPU implementation and the GPU implementation, which worked well on both larger terminal set, which is what the main motivation for us. So whereas the third work, which did not have which did not run, or which was not able to run on larger set of vertices, and that is what we are actually addressing. And not just that, in terms of time, we wanted to reduce the time comparatively with respect to the other baselines we have. Right, so yeah, so we were able to produce this same or similar quality as that of the JEA's paper. Right, okay. So what are the challenges in parallelizing this KMB? So graph algorithms in general have this irregular access pattern, so which is not easily parallelizable, right? Right, okay. So there is KMB involves multiple primitive algorithms. So by primitive algorithm, what do we mean? It has a single source shortest path as a subroutine. Similarly, it has a MST minimum spanning tree computation inside it. So when there are multiple primitive algorithms are involved, we need to actually interface to algorithm and change the input accordingly. So there is a dependency in passing the graph from one algorithm's output to the other algorithm's input. So this is a challenge. So maintaining consistent parent information in the single source shortest path is a challenge. So even the popular framework for GPU graph library, Gunrock, had this issue of having a consistent parent information. So an individual atomic instruction actually may not actually lead to an atomic transaction. So we will get to this challenge and how we overcome this challenge in a couple of slides after. But so this is the last challenge we had is the parallel KMB may not output may output a different solution during different invocations. So it is unlike other algorithms, for example, as single source shortest path, we cannot compare the values one on one with the sequential implementation. So it makes it difficult to validate the solution by doing some other additional work. So what is our contribution? So we have a optimized CPU implementation for KMB algorithm. Similarly, we have an optimized GPU implementation for of KMB algorithm. So we use a novel technique which we call it as SSP Hall technique, which actually has improved the performance of our CPU implementation. Similarly, we have a novel technique which we call again p-SSSP technique, which means that multiple parallel single source shortest path algorithm is run in parallel. So there is like parallel SSP is being run in parallel from different sources. So so the CPU implementation actually improved the performance, got a speed up to 15x over the JEA's KMB, and similarly we got a speed up of 27x over our CPU implementation, which is the current best CPU implementation for the KMB. So similarly we got a 62x speed up with over the JEA's KMB version. Okay, let's introduce KMB to everyone. So what is KMB algorithm? So KMB is a three-phase algorithm. What is the first phase? So first phase, compute shortest path distance between every pair of terminals, right? So so it computes shortest path distance every pair of terminals and construct two graphs, namely G prime and G double prime in the subsequent phases. So what is G prime? G prime is nothing but a complete graph on the terminal vertices. And what are the edge weights? So edge weight of this complete graph is borrowed from the previous phase, which is the shortest distance between the pair. So that's how we construct G prime. So every edge in G prime actually corresponds to a path in G. So the final step in phase 2 is to run MST on this G prime, right? So we get a tree out of it. So for each edge that we got in the tree, so we substitute that particular edge with the corresponding shortest path we had in the phase 1. So we basically collect all the edges and vertices along the shortest path and construct G double prime. So finally we run G and an MST on G double prime. So this is the KMB algorithm. So we'll run quickly and run through the algorithm using this example. So we are going to show you two different execution of the same algorithm. So what is the first step? First step involves the shortest path distance between every pair of terminals. So the terminals here are A, C and B. Notice that the example is designed in such a way that between every pair of terminals we have two shortest path. So the algorithm is free to choose any one. So we are going to, on the top configuration, we are going to choose for example shortest path distance for A and B is via C. So shortest path distance for A and B is via D, and so on. So what is G prime here? G prime is a complete graph on three vertices, which is K3 triangle here, and since all the distances are same, it happens to be 10 in all the case. All the edge weights happens to be 10. So let's run MST on that. So let's say MST chooses the same set of edges for both the configuration, top and the bottom configuration, and let's expand those edges. So this is phase 3. So let's say we'll expand the edge AB with respect to the shortest path we have captured. So this shortest path is expanded as the this way, and this shortest path A and B is expanded via D. Notice that for the same algorithm, two different execution is possible, and yeah, so the optimal value we got for the bottom configuration is 15, whereas the top configuration is 10. So a parallel KMB may output a different answer when there are multiple shortest paths between two terminals, right? So this is what we wanted to emphasize through this example, and notice that our G double prime here is itself a tree. So the last MST, the final MST which can be avoided, right? Yes. Okay. Let's move on to the description of the KMB algorithm as given in their paper. So notice there are two for loop running over the terminals computing the shortest path distances. Notice that we also need to record the weight of the shortest path in order to compute this G prime, right? So then we run a minimum spanning tree, and similarly using the edges in the spanning tree we construct G double prime, and we construct G double prime and using the vertices along the shortest path distance. So then finally there is the MST. So these two loops can we avoid these two loops? Yes. So we modified their algorithm and substituted with single for loop, but instead of running shortest path distance we run single source shortest path algorithms. So we replaced shortest path with SSP algorithm here, and then rest of the algorithm remains the same. But notice we only wanted shortest path information from one terminal to other terminal, right? But this SSSP runs to completion. So by completion, what do we mean? It runs from a source to every other vertices, every other n-1 vertices, right? Yes. This is what a chance of improvement, and this is what actually we have implemented in our optimization. Okay, so before we get to that, so how do we parallelize this algorithm? So one naive approach would be to replace all the SSPs and the MSTs here using a parallel algorithm. So that is one possibility, right? But each of the parallel SSP will run one after the other. So which means that each of the parallel SSPs will run one after the other, since we have to run for all the terminals, right? So our novel aspect here is like we designed our GPU implementation such that we have a tunable parameter such that we can run multiple parallel SSPs in parallel. So yeah, so we'll get to it. So before we get to it, we'll quickly cover some basics that will also help us understand our GPU optimization in detail more. So okay, so there are two different algorithms for SSP. One is Dijkstra's and one is Bellman-Ford. Dijkstra's runs slightly longer, whereas Bellman-Ford runs slightly longer, whereas Dijkstra's runs comparatively faster. It uses a heap data structure, whereas Bellman-Ford does not use a heap data structure. So what does Dijkstra do? It picks up one node from the queue and it relaxes all the neighbors along the way. So this is the main operation that we will be doing. We'll take a particular node and relax all its neighbors. Yeah. Okay. So this whereas Bellman-Ford is like at most n-1 times we actually relax all the edges. So we use Bellman-Ford in our GPU implementation, whereas we use Dijkstra for our CPU implementation, because it is difficult to imitate a queue data structure in case of a parallel setting, right? So this will be the Dijkstra's operation. Very quickly we'll what is the input? G and this G along with the source. So what is the output? Distance and also the parent array. So the parent array is otherwise called as predecessor in the literature, right? Yeah, so we initialize this parent arrays and the distance array to sentinel values, and we initialize the source's distance to 0. So notice these are the important pointers which we will be using in our optimization technique. Okay, so as we said earlier, Dijkstra picks one element from the queue and relaxes all the neighbors. So okay, so Okay, so let's go to the CPU optimization that I was building up. So this SSP runs to completion, right? So it starts from the source and it computes distance from the source to every other n-1 nodes, right? So we don't actually need it. So this is an additional amount of work that we are doing. So that is what we are able to identify. And if we somehow stop the SSP when the last terminal is visited, so basically we want all the distance from a particular terminal to every other terminal, right? So if we somehow are able to stop halt this SSP when all terminals are visited, that is what we wanted. So this we are able to achieve using the Dijkstra property. The property is the following. So when a node is picked up from the queue for processing, the distance of that particular node is saturated using all the visited nodes, right? So this actually made us possible to actually halt the SSP when the last terminal is visited. So this significantly improved the performance of our CPU implementation, right? So yeah, so these were the design choices we had for parallelizing the KMB algorithm. So notice that the first option we have already discussed. So what does it do? It runs a sequential single source shortest path algorithm k many times and followed by 2 minimum spanning tree computations, right? So this is the first version of our GPU implementation. What do? What we replace all the primitive algorithm with a parallel primitive algorithm. So notice that this algorithm, this version 1 of our GPU implementation actually outperformed our CPU implementation, even without the SSP halt optimization that we did for our CPU implementation. So okay. So what are the other ways to improve our version 1? So although this SSP happens in parallel, so the k SSPs that are happening is happening one after the other. So which means it's happening sequentially one after the other. So we try to improve this algorithm, version 1 of the algorithm, using the following 2 of the following ways: by replacing the sequential SSPs and running all the k SSPs in parallel. The other thing is, like, we can run parallel SSPs and also in parallel. So this is what we were able to achieve. In some sense, we have a tunable k value such that we can specify that to run we can make the algorithm run this many parallel SSPs in parallel, right? Okay, so how does a ideal GPU implementation of an SSP would look like? So it will be launched with n threads. So one thread will be assigned to each vertex. So it performs relax on in parallel. It relaxes all the neighbors in parallel. So how long we should do? We should do till all the till there is no change in the distances. So in some sense, it is like pushing the data from the source to every other vertices. For example, node 1 actually pushes the data from itself to all the neighbors. So we call this implementation as a push based SSSP, right? So this is a standard implementation of SSSP. So this do while loop here, which actually computes the SSSP, we just have to make this run for all the terminals. Notice that we reuse the distance and the parent arrays across iterations, so that the memory is reused and saved. So also notice that we need parent array information or the predecessor array information, because in phase 3 we need to know the intermediate vertices along the path. So it is essential to calculate the consistent parent array information in the shortest path computation, right? So let's look at the SSP kernel more carefully. So there is a for loop running over all adjacent vertices of U. So basically we are updating the distance atomically here when there are when the distance gets updated, which basically translates to when the atomic min is success, we just update the parent of that particular node. So is this enough? So this code is buggy. So this is not enough because we have a challenge here to update in updating the parent array. So let's look at more carefully what is this challenge. So when two threads are trying to update a common neighbor v, and let's say 10 is the distance from source to v in the previous iteration, and both 1 and 2 are trying to update the distance to some other lesser value. Let's say thread 1 operating on vertex 1 is trying to update the distance from 10 to 7, and thread 2 is trying to update the distance from 10 to 5, right. So this in this kind of situation, this code will fail. Okay, so we'll get into more detail and how we'll find out how this happens. So okay, so notice that the distance arrays and parent arrays are shared across the threads. So okay, so on the left hand side we have the execution of thread 1, and the right hand side is the execution of thread 2. So at the first two, after the first two instruction, both will have 7 and 10 as the new cost and the old cost. Let's say if this statement is executed by the thread 1 first, then the distance of v will be updated as 7, right. So old will be 10. So before we get to that, ideally we wanted, what do we want? We want the distance of v to be 5 at the end of this step, which is the least value, and we need to know that the predecessor the predecessor value for v will be 2, because it is via 2 the distance is 5, distance to reach v is 5, right. Yeah. So with this knowledge, so let's say if thread 2 executes this, and again it updates from the previous previous distance values from 7 to 5, right. So notice in both these cases the atomic min happened to be a success. Let's say thread 2 gets to update the parent value first, so which is the actual parent value which we wanted, but then when thread 1 executes the same statement, we are getting an inconsistent parent information for v. Although the distance information has said to be 5 correctly, the parent is wrong. So how to update both the distance and the parent information at the same time? One way to get around is like using locks, but using locks is a costly operation in GPU. So it is notice that this scenario we are showing is we have shown only for 2 threads, right, but in general it could happen for multiple threads. So it is a challenge to find out which thread is updating the dv to be minimum, so that we can update the parent array accordingly. So yeah, so we overcome this situation with a very simple approach. So instead of doing a push based approach, we use pull based approach. So all our graphs are undirected, so we have highlighted these changes. So with minimal changes we are able to make the push based implementation into a pull based implementation. Again, in a pull based implementation, what does it do? It pulls the information from the neighbor and it updates the distance of that node. So notice in this case we have avoided atomics, so thereby the overhead of atomics is removed, and thereby we get improved in the performance, and more importantly like we are able to update the parent information and get a consistent parent information without any inconsistent update, as we shown in the previous slide. So it is possible because one thread is writing to a particular index, right. So these are the optimizations that we tried out, and these optimizations are for SSP, a single source shortest path algorithm. So the one that are highlighted is what worked best, and when used combined all these highlighted, we are able to get a better performance for the single source shortest path algorithm, right. So since we discussed pull and push already, we'll start with the compute optimization. So graph algorithms in general are memory bound, so there are lots of load and store operations that do happening in an irregular fashion. So it is essential to do this compute optimization. So each thread, so in a pull based work, so each thread is performing relax on the neighbors, which could be delta many work, right. So delta is the max degree on the graph. So like what if we give more amount of work, so instead of updating its neighbors, why don't a thread update neighbors of distance as well, neighbors as well, sorry. So that is delta square. So delta square did not perform well, whereas by repeating the work, so by repeating meaning, so it's doing the same work again and again. So let's say we relax the neighbors and relax the neighbors one more time, so which we call it as T delta. So this unrolling operation actually benefited when compared with a single del and del square computation. So empirically we were able to find out when T is 3, our performance actually peaked. So there are other optimization, compute optimization that we tried, that is data driven and edge based optimization, where data driven involves keeping track of active nodes and launching only that many threads, and whereas edge based involved launching m many threads and relax one edge at a time. So both were not performing that well compared with the TDEL optimization that we had, right. So memory optimization, so in case of 3 pull, that is performing pull 3 times one after the other, so we have to run over the adjacency, the neighbor information thrice, right. So accessing the neighbor information from DRAM might be costly, whereas we have this programmable shared memory which can be thought as a cache. So basically we can copy the neighbor information to this shared memory, which shared memory, the accessing shared memory is faster when compared to the DRAM. So it has significantly improved the running time in our case. So yeah. So there is one caveat here is, like when we use 512 threads per block, so we can only store 24 words per thread. So when a particular node has a degree larger than 25, then we shared memory may not be, will not be useful in that case. So but in general, as our the degree of a node is very sparse, so we are able to achieve get a 25% improvement over the 3 pull implementation, right. So here comes the fun part. So this is so far we have seen whatever optimization for SSSP. So this optimization is what we did for the KMB algorithm itself, right. So yeah, so SSP happens in parallel. So to run 2 SSSPs, we have to run one after the other, right. So instead we use double barrel approach. So what is double barrel approach? So double barrel approach is like we run 2 individually parallel SSPs also in parallel. So it works just like this rifle. So we load 2 bullets in the and we will have only one trigger to fire both the bullets, right. So that's basically what we are doing in our double barrel approach. So this can be generalized to any p-SSSP, where p here means that number of parallel SSSPs which we can run on. So this we have a tunable knob to tune in to set what value we with what parallelization we need to run on, right. So to understand more about this double barrel approach, so this is the distance array and this is the fixed point computation we have. So to load to mimic loading of 2 bullets, we basically double the distance arrays, which is so we are highlighting the changes that we did in yellow. So we basically double the distance arrays and also launch 2n threads instead of n threads. So similarly, you notice that the first array the source is S1, and for the second array the source is S2 or source 2, right. So we need to set the initialize the distance accordingly based on the index. So yeah, so this is with this information, with almost no change in the kernel, we are able to run multiple SSSPs, multiple parallel SSSPs in parallel. So yeah, so the key takeaway here so far is solving Steiner tree problem is NP hard, yes, and we have a KMB algorithm, which is a two approximation algorithm. That is what we have implemented both on CPU and GPU, and CPU implementation greatly benefited from SSP halt optimization. So then SSP had a parent update issue. I mean, the updating the parent was challenging, but pull based SSSP actually overcome that challenge, and our GPU implementation, like even without the SSP halt optimization, was performing way too better. And we have this novel technique which we call parallel SSPs running in parallel, like so. So these were the things that we have seen. So let's get to the experimental setup. So these are the configurations that we have used and the softwares that we have used, and yeah. So these are the set of graphs that we have used. So we have used 14 graphs, of which 11 we have taken from Pace Challenge, which is the largest and the difficult instance from the Pace Challenge, and we have taken two hard instances from Steinlib. Steinlib is the collection of all the Steiner tree instances known so far. Yeah, so one instance we took from Snap library, and yeah, so these are the range for our n and m and k values. So we use two baseline, one is the Pace winners code and the other is the work published in Journal of Experimental Algorithm, which we abbreviated as JEA, and rest of the plots that we are going to see, right. Okay, comparison of solution quality. So why do we need solution quality? So yeah, so our algorithm, so the problem we are working is NP hard, and our algorithm is an approximation algorithm. So we don't generally reach the optimum solution, but our algorithm produces a solution which is closer to optimum. So it is not only we should quantify the running time, we should also quantify the solution quality in our case. Yes. So our GPU algorithm and CPU algorithm along with the JEA was performing similar in terms of quality when compared with the optimum solution. So the optimum solution here means the optimum value of the Steiner tree, which is given by the organizers of the Pace Challenge, right. So the GPU optimization and CPU optimization are performance wise, I mean the solution quality wise, better than the Pace winners code on all the instances of the Graphsuite we have taken, right. Yeah, so we'll move on to the running time. So to get a glimpse of our running time, so we plot the speed up with respect to our CPU over the JEA implementation, and also GPU implementation over JEA implementation for all the 14 instances on the x-axis, and the speed up along the y-axis. So we also plot the GPU optimization with respect to our CPU implementation, because currently the best CPU implementation is the implementation that we have for KMB, right. So notice that consistently it was both our CPU implementation and GPU implementation performed better than the JEA in terms of running time. So for example, if you look at carefully, then for T11 instances JEA actually timed out. So the timeout we had is what 30 minutes, which is the hard timeout that Pace challenge organizers kept for their challenge, and we have replicated the same in our setting as well. notice that our CPU implementation, which actually terminated well within 30 minutes and produced the answer for T11 instances, which would not have happened if we had not incorporated that CPU, SSP halt optimization that we talked about a couple of slides before, right? Okay, so when let's compare the GPU time. Each of the bars specify the running time for each of the individual optimization that we had. Notice 2-SSSP means a double barrel approach, and p-SSSP means for what p value the performance was at its peak. So when combining all these optimization p-SSSP, 3-pull and along with the shared memory, on an average we are able to achieve a good performance when combined with all this optimization. So one other thing to note here is this T14 graph, which we took from Snap library, did not get benefit out of the shared memory optimization because it was having large number of the average degree of the graph is large. It's more than 24, right? So on an average, combining these optimization actually performed best for us. So one other important thing to note, and we also were surprised because of this, is when we increase the number of concurrent SSSPs to beyond a range, then we were able to observe this pattern of the performance. The running time kept on increasing, and then it started running time kept on decreasing, and then it started increasing after a certain period of time and then tapering out. So for this we have plotted only for T14 graph, whereas this is the case for all the 14 instances. So the optimal the performance was its peak when it is somewhere between 16 to 64 for all the graph instances that we have taken. Yeah, to understand the scalability of our implementation, so for T14 instances which did not come with the predefined terminal set, so we have an option to choose the terminal set randomly. So we chose the terminals randomly from 500 to 5000 in steps of 500, and we run both our GPU and CPU implementation on all the instances, and we were able to observe a nice thing, which is the following. So our GPU implementation was scaling very scales better than the CPU implementation, because as we increase the number of terminals, the number of SSPs we need to run also increases, right? So whereas if we look at our GPU implementation, so it greatly benefited from our p-SSP optimization, that is running multiple SSPs in parallel. So it is due to that we were able to get a better scaling when compared with the sequential CPU implementation, right? I'll just summarize whatever I have. Okay, so SSP halt optimization greatly benefits the CPU version, and pull based optimization and p-SSP optimization greatly benefits our GPU implementation. And yeah, so the Steiner tree that we are outputting can be used as the initial tree for other local search algorithms, right? So since we are able to produce a Steiner tree in a quick time, this tree can be used for other local search algorithms. So and one thing to remark here is our p-SSP technique, right? So this technique can be applied to every other place where multiple parallel instances of the same operator being applied. So this can be extended to wherever that multiple operation needs to be applied also in parallel. So this is the summary. So with respect to the future work related to this, we can extend the CPU implementation to a multi-core CPU setting as well. So similarly, we can extend the GPU implementation to a multi-GPU setting as a future work. So this is with respect to this work, and with respect to the PhD work, we are looking at a capacitated vehicle routing problem, which is also on the similar lines of whatever we have done. So ultimately, we wish to build a GPU graph library for aiding the NP-hard problems. So yeah. So with this, I conclude the presentation, and thank you for your patience. And if you have any questions, feel free to ask now or like offline as well. So I'll be happy to answer any questions.